Good day, everybody. So I know that you are relaxed after the food, and now I have to talk to you about some difficult technical stuff, but I will try to make it as easy as possible. Of course, I will talk about technical details. So it's a result of our last research grant. It's a new grant, only 6 months have passed, and these are, if to say truth, our first results. So let us begin with the basic concepts of cryptography. Let's cover them quickly for everybody to follow me. So in cryptography, as always, we have our two heroes, Alice and Bob. First of all, they have to generate the key and to share it. So Alice generates it and sends the key to Bob. Now we are talking about symmetric cryptography, so private key encryption. So Alice takes a message and sends, encrypts the message by means of her key using the, as you can see, encryption algorithm, and sends the cipher to Bob. Okay, Bob received the cipher, and as he has the key, he can, I will take the letter from here, I think, and he can decrypt, yes, the cipher by means of his key. Here we have Mr. Hacker that is looking at cipher and trying to get the information. We say that the scheme is perfect secret if the hacker, when looking at the cipher, doesn't get any additional information about the message. The only thing that must be true that after decrypting the encrypted message, of course, we must get our message back. As I talked about perfect secrecy, one-time pad is a scheme that has perfect secrecy, and it uses XOR. Here quickly is explained what is XOR. It's a bitwise operation. When we XOR 0 and 1, we get 1, and when we XOR the same values, so we get 0. So how one-time pad work? We take the message n bit long, we generate the key of the same size, and we just XOR key and the message. To decrypt the message, what we do, we just reverse the operation. We XOR key and C. Now here it's shown that it's really true. Key XOR key is 0, and we are left with a message. Here it is illustrated how it works, n-bit key and bit message, and we get n-bit ciphers. Why it's so good? Why it's not used in practice? It was used, for example, it was a phone line between Washington DC and Moscow, but now it's not used in practice because of two big problems, because the size of the key must be really big, because it must be of the size of the message. Today in real life the messages are really big, and it's one-time key. What does it mean? That it's secure if we use the key only once. Now here is a little proof that we cannot use the key twice. So here is the first cipher, the second cipher. The first cipher is got by encrypting the first message with the key, and the second cipher is got by encrypting the second message with the same key. When we XOR the ciphers, once more key XOR key, by XORing key with the key we get 0, and we are left with a XORed message. So if we have two ciphers, we can just XOR them and get the XOR of the message. So we leak some information about M1 and M2. Okay, we got it, but is it significant? Yes, it is. Because first of all, it's not longer perfect secret. Okay, it doesn't seem that it's really serious, but we will see it now. Also, when we XOR M0 and M1, we see where the messages of the bits differ. Because if they differ, we will get the 1 XOR, and if are the same, we will get 0. We can analyze the frequency and also exploit the characteristics of ASCII. Here is ASCII table, and what is interesting here, that every letter in binary begins with 0, 1. Every space begins with 0, 0. So if we XOR two letters, we get 0, 0, but when we XOR the letter with a space, what we get 0, 1. So it's very easy to identify when we XOR the letter with a space. Here is just a real, the little example for fun. We have two ciphers, we XOR it, and here is the XOR that we got. Here only 2 bits are shown. What it gives us? It gives us the information that we XOR the space with a letter, yeah? Because it's the same that XORing 2 messages, like we proved. So let us try to recover the letter. How we can recover it? For example, the XOR ciphers gave us this value. We know that this value is got by XORing the space with something, and XORing back we can easily identify that it's the letter P. Okay, as we said that the key must be really big. For this we have pseudo-random number generators. How they work? They take a little seed and afterwards enlarge it with a big output. This pseudo-random number generator, I will call it OQRNG, can be used in one-time pad. In this case, perfect secrecy we will not have already, but we will have still security, but different one, computational one. So here the key we have n bits, the message we have p bits, where p is much more than n. We apply pseudo-random number generator to the n-bit message, and afterwards we XOR the message with pseudo key and get p-bit ciphertext. Okay, very good. Afterwards we got the revolution of public encryption. Here Alex already generated 2 keys, the secret one and public one. The public one she stores in some public repository, open one, and by means of this public key, Bob takes it and encrypts the message. So everybody can encrypt the message. In this example, Bob can, and he sends the encrypted message to Alice, and only Alice can decrypt it. Why? Because she has the secret key. RSA is the example of a public crypto system. Here Bob generates the key. N is a multiplication of 2 prime numbers. The public is n and n, secret is d. So he gives the public key to Alice. Alice encrypts the message, and afterwards Bob decrypts it. No, it's just how RSA works. Let us say a couple words about digital signatures, because we will use them in the results. So it's a really key technology for making the internet and other IT infrastructure secure. They provide authenticity, integrity, reputation and of data. So having the really secure digital signatures is very, very important in practice for cryptography. Yeah? The signatures that are used in practice today are RSA, that we just talked about, DSA, ECDSA. Okay, we begin to work. I want to say once more that what I'm talking today is post-quantum cryptography. It's not quantum, it's post-quantum. It's the implementation of new crypto systems, yes? So we began to work on it when we saw that Google signed a contract with D-Wave, that they began to create quantum processors, yes? That create a qubit, each qubit double the calculation speed, so these quantum processors can make the tasks that classical computers cannot. And what they can do, they can break our RSA. They can break all the crypto systems that are based on mathematical problems. And for example, RSA is based, as we said, on factorization problem, and it can break it. And as you know, RSA is used everywhere in all the protocols. Also, it's underlying protocol. It's used in underlying protocol protected internet communication like SSL, S1. It's used in universities, in government organizations, and so on. So breaking RSA, as you can understand, will cause real house. Now, on October 2000, now in October 23rd, we got very interesting news that Google said that they have reached something called quantum supremacy. So they created a computer that is called Sycamore, that solved very difficult problems in 200 seconds. When they compared it to best classical computers that was released by IBM, and it's really big, it's like two basketball courts, they said that IBM would break it in 10,000 years. So they showed that the computer is really quantum and he can do something interesting. And by the way, they concretely made a random number generator by means of it. Okay, IBM didn't like it so much, and they said that Google lies a bit, and they don't need the computer that is called Summit, doesn't need 10,000 years for it. It just needs 2 days and a half. And what Google did is not a big deal. We do have different RSA alternatives. Here are the list of them: hash-based digital signatures, code-based, lattice-based cryptography, multivariate, public key, crypto system. Last year I was talking about lattice-based, but no, the integration with hash. And today our results are only connected to hash-based digital signature schemes. So let's talk about them today. Okay, we have alternatives. So what to do more, but we have the problem because these alternatives are not efficient enough and they are not safe enough. For example, there was an attack, the successful attack, implemented by Neil Costigan, the student of Dublin City University, with his professor together, Michael Scott, and 4 more countries were involved in this attack, and this attack was able to recover the key in some 8,000 hours of CPU time. What the scientists answered about it, they said that the key wasn't enough and enlarged it. So no, it's already a big problem when it's hacked, yeah, it's attacked. Also must be emphasized that this system cannot be used to encrypt the same message twice and to encrypt the messages when it's known the correlation between them. Okay, the efficiency spectrum is also very important. Inefficient cryptography can be okay for us, but for the server that handles 1,000 processes per second, it is impossible to have inefficient cryptography. So let us talk, as I promised, about hash-based digital signatures. As we know, it's impossible. It's very important because quantum computer breaks RSA and other digital signatures that are based on difficult mathematical problems. And these hash-based digital signatures, they use just the hash function, and the security is based on the collision of this hash function. So first of all, name for DFE one-time signature was proposed. There we have signature keys and verification keys. The signature, we have n pair, so 2n signature keys, n pairs of signature keys of length n. To get the verification key, we just apply one-way function to it, and here's how it's got, and get verification key. Okay, to sign the message, we look at the message. If the first bit is 0, we take the first element from the first pair, and if it's 1, we take the second element. This signature length that we get is n squared. Okay, to verify the signature, what we do, we apply the following equality. So we apply one-way function to our signature and compare it with the hash of our message. Why hash? Because the message can be of any size. First of all, we hash it to get the n-bit message, and are working with it. In the case of Lamford, to achieve the minimum security of 2 to the 18, the total size of the keys must be 51,000 on the 200 bits. That is 50 times larger than in the RSA case. And also, as I said, the signature length is much bigger than in the case of RSA. Okay, Internet one-time signature scheme was offered to reduce the size of the signatures. But these one-time signatures aren't convenient in practice because too many these signature and verification keys, yes? And it was proposed Merkle crypto system where the public key was the public key replaces all these verification keys. Yes, and the public key is the root of the tree. Okay, how it works? The length of the key of the tree is chosen to be h more than 2, and with one public key it is possible to sign 2 to the h documents. And are generated xy and yy signature and verification keys in the same way like I talked to you. And afterwards the hash values of the verification keys are calculated, and we get the nodes of the tree. Now look how it works. So we hashed these verification keys, got 2 nodes. Afterwards we concatenate them, hash the result. Afterwards, so we concatenate them, hash the result. We got 2 results, we concatenate them, hash the result, and like this we go to the upper node. The only thing what we know that every write node for example, for this node node is called flatten one, or authentication node, so ours. This node is a flatten for this, so every right node is a flatten of the left node. Okay, how it works, how the signature generation works. First of all, we get the message, we hash it to get the n-bit message. Afterwards, we generate one-time signature by means of Lamford, and we alternate how we want. For this we choose any signature key. With this we begin, yes. Afterwards we calculate the verification key, and our signature is a concatenation of this one-time signature of our public key. What is public key? It's our root of this index of verification key, and all these anosys, all these flatten nodes, all these anosys, so every write node. As you see, here we have a lot of one-time keys, yes. So not to generate so many signature keys was offered to use pseudo-random number generator. So it will take the seed, and by means of the seed it will generate all these parent keys. So here how it works: we take the seed, apply it to parent G, get the new seed, and get the random number. And by means of this we get all these signature keys. So we use only some little seed, and afterwards get all these signature keys. It must be integrated into phases once when we generate the keys, and afterwards we need once more these signature keys when we sign the message. Yes. So what is great help here, that we don't save so many signature keys in the memory, very big ones. We need to save only one seed, but it has the problems. Let's talk about them now. What are these CSPRNGs? They are the pseudo-random number generators that are used in cryptography, that are considered to be secure in cryptography use. For example, Bloom-Micali and Bloom-Shard generators are used very often in cryptography. And these CSPRNGs are based on number theory. Yeah? For example, here is the example of how SHAB works. So its next output works recursively, so we get it from the previous one. And so xi plus 1 is xy squared mod n. And what is n? N is the product of 2 prime numbers. As the seed, it gets first of all, as the input it must get the seed, and it must get x0. It must get the seed x0, and it must get n. The only very important thing that initial state x0 must come from true random number generator. Okay, there was the article. There were published the results that quantum computers are able to break this type of parent keys. Concretely, they were able to break Bloom-Micali parent key. The attack on it was shown. It was using Grover algorithm, and it was able to reveal all the key to recover all the key. So this type of attack can show to us that this type of PRNGs that are secured against classical computers cannot be secure against quantum computers. We offer to use PRNGs that are based on hash. These PRNGs are HDBRG and HMACDBRG. They are NIST standards, so they are absolutely secure, and they use a hash function. It's very convenient for us because in our Merkle tree we use the hash function. We made the comparison of it, and HDBRG is much more efficient. And as we know, it must get the really random seed, and we decided to integrate the seed that we get from quantum random number generator. Okay, what are quantum random number generators? In 1961, the researchers offered to use quantum phenomena as a source of randomness, and after it they began to use it a lot, to work on it a lot. And at that time, radioactive decay was already a particularly accessible source of true randomness. Geiger-Müller tubes were already sensitive enough to capture and amplify alpha, beta, and gamma radiations. At that time, mostly beta radiations was used. In a Geiger-Müller detector, a single particle makes a ionization effect that afterwards is amplified in a Townsend avalanche. So we get a device that creates a pulse for each detected particles. And the time of detection of this particle is exponential random variable. And the probability of getting the pulse can be shown by this formula. And must be emphasized that the number of pulses that occur in a concrete time period follows a Poisson distribution. And we can show experimentally that these pulses occur in independent time. And the probability of finding 10 pulses, here it is, where lambda is a mean number of pulses detected in 1 second. These OQRNGs based on radioactive decay have a lot of common features. Mostly all of them have the counters, but by means of these counters, random number are the number of pulses are converted into random numbers. When the device gets the new pulse, it raises its counter, and in some concrete time, it resets it to 0. And another important element is timing with a digital clock. If we say that f is a frequency of the clock, when f is more than lambda, we say that it's a fast clock. So it generates a lot of pulses in pulses in some concrete time. And if f is less than lambda, then we say that the clock is slow. The randomness in this type of generators can be converted into random values in different ways. For example, Vincent and the Isida and the Ikeda and Vincent generator use the fast clock. So they get the impulses, and afterwards the impulses are converted to random numbers. Okay, the sequence is not random, but the distribution of the values must be corrected. For example, the Schmidt generator, it uses the slow clock. So when the clock produces a new pulse, the generator increases the number, and in some period it resets it. If we must get the values from 0 to v minus 1, we just use modular V operation. If we use v equal to 2, we can get just binary, so we can get 0 and 1s. Of course, in this case, the distribution is also not uniform. But when we use mod operation, we get only the very small bias. Okay, today almost all existing quantum random number generators are based on quantum optics. Why? Because the parameters of the light, of the quantum state of the light, have very good property, have very good randomness property. So they give us the opportunity to get very good implementation. For example, light from lasers, like light-emitting diodes, single photons, are very affordable and convenient alternative of radioactive material, and are wonderful source of quantum randomness. Today we will use time of arrival generators, and they are the representatives of optical quantum random number generators. And why we talk a lot about radioactive decay? Because their principle are very similar to the OQRNGs that use radioactive decay. Okay, how do they work? They have a rather weak source of photons, and they have a detector and a timing circuitry that raises the time of each detection. So the detector receives photon from lab in coherent light and from the coherent state from a laser. And this time is exponential value. We are just taking the timing intervals of getting two pulses, and afterwards, if the first time interval is t0 and the second one is t1, we take the difference. If t1 is more than t0, we assign to a bit 1, and in the opposite case, we assign to it 0. Of course, there is very little probability that t0 will be equal to t1. It's very small probability, but this case we also consider. We use it in our implementation, and of course this t1 and t0 are not integers. Yes, they are some kind of float numbers here, but we convert them into integers. In 2007 was offered the first optical quantum random generation that used time detection. It took photons from the LED. So we offered to use time arrival quantum random number generator as a seed of hash of the BRG. And here is a scheme what we do. So in the key generation we don't generate all this exercise. We just take one quantum seed, pass it to the PRNG, and afterwards get all these signature keys. All the other process is the same, and in the signature phase we need the signature keys once more. So we take the same seed from quantum random number generators to get the same keys, and by means of hash DBRNG, that is NIST standard, we get all the signature keys. And the signature verification is absolutely the same process, because here we don't need these pseudo-random number generators at all. About the security, of course, the system is secure, because what we changed in the classical Merklein, we only integrated here the pseudo-random number generator that is quantum resistant, because it uses hash functions. As you will see, we used here SHA-512, and as a seed, it gets a really random seed that is got from quantum random number generator. Yeah. So we have made the implementation of it in your familiar Python. Separately, we made the implementation of DRPG and of quantum random number generator. Here we are importing them. Okay, nothing interesting here. As you see, we are getting the seed from quantum random number generator, and afterwards we are passing it to our DRBG. It was the key generation phase. In the signature phase, what we do with the same seed of the DRBG, we generate the same signature keys. And as you can see, we use tuple here, and afterwards we are just deleting it immediately. And as I said, that the time intervals can be the same with very little probability. Now we check if they are the same, we just reseed it. Here is efficiency of the scheme. No, it's rather good. It checked for 128 bits message. Here is the same Python implementation of it that I showed. Yes. Here it works rather fast. No, of course, for little signature. And okay, that's it. That's what we made. And if you have some questions, welcome.
Okay. So for what I understand, you use quantum random number generators to improve the security of existing encryption algorithm. That is right?
I use it to create the seed for pseudo-random number generator, and I do it, of course, for make it real, to have it really random one.
Okay, because if we use a random key, we can decrypt it at the destination. That is the problem. So we cannot use directly a key generated by a quantum random because we cannot decrypt the message.
You are absolutely correct. Because of it, we use it as a seed to the pseudo-random number generator. And we are using the same seed, and afterwards pseudo-random number generator gives us the different pseudo-random values. Very good question. Thank you.
Thank you. So the nice thing of that is we can adapt the quantum random number generator to existing encryption schemes.
Yes. Okay. Here, how it works.
Thank you. Thank you.
Yeah, so I have a question about the actual generation of the seed. Do you know if there's a commercial implementation right now for such devices, or what do you think is the estimation of the cost of a?
By the way, there do exist quantum random number generators. They do exist. They are checked and so on. So, as we said, from 1961, they began to use the quantum phenomena to get the randomness.
And this is
so, and what is interesting, we are thinking of buying a couple of them and bringing to Georgia for experiments.
Thank you.
Hi. Do you have any implementations that you have done on hardware security modules with this schema?
No. It's a new result. It's a new result that what is done only the software implementation for now.
So only software right now?
For now, yes.
But do you plan any integration with any hardware security module provider?
I think yes. I think we will try it. First of all, we have to bring this to buy these quantum random number generators, to get the seed from them, afterwards to apply here and see how it works in real life.
Is it something that you see it in the near future? I mean,
if we get the finances for it,
okay,
we are working on it, so I hope that yes.
Okay, thanks.
As I understood, you are using quantum seed in PRNG, and can you change the size of the seed if it's necessary?
Yes, yes, it's dynamic. Here is shown. Here you can see that I specify the 1 minute, I will enlarge it. Here you can see that I specify the size and I pass it to the QRNG.
Okay, thank you.
Okay, so suppose I do get my hands someday on a QRNG. How may I go on and prove that it is indeed a QRNG and not a PRNG?
How it can be the PRNG because it's a hardware and it's quantum one.
Well,
Yes,
let's say that
it
someone is
uses
selling it to me as a service, so I don't actually get to see it physically. How do
yes,
I sample it and prove that it's...
but as I said, in 2007 was offered already the first commercial ones, and they are effectively sold, and the physics proves that it's really quantum random number generator and so on.
Okay, thank you, but what about 50 years from now, let's say?
About what?
50 years from now, when I will be able to get a generator as a service, so not as a physical appliance, how can I sample it and prove to myself at least that, okay, it is truly quantum and not just a PRNG or whatever?
I understand what you say. For example, the Google News that I talked today, yes, they concretely showed that they created the new random number generator, the quantum one. IBM says that it's not so special as they say, but nobody says that that is not quantum. I read a lot of articles, a lot of discussions about it, and what the experts say, they said that they did really get the quantum one. The only problem that there is that they are still far away from implementing Grover and Shor's algorithm.
Okay, thank you.
So as we see, it works. Thank you.
How easy do you think it would be to integrate a quantum number generator with today's classical computers?
I think that in any case it will be a good idea, because we can see that a lot of PRNGs are broken. Yes, theoretically, of course. Once more, this Grover's algorithm is for now only theoretical, but we can prove that a lot of PRNGs are broken. Yes, so in any case, to have the quantum randomness in today's scheme is rather good idea, because maybe tomorrow these quantum computers already will be in practice, yes, and they will maybe break our existing PRNGs and all this stuff, yeah.
And follow up on that, how hard would it be to build a quantum number generator at home?
At
home?
I think it will be hard, yeah, but I don't have any. I'm going to buy, so I don't think that it's too easy.
Okay, thanks.
Thank you.
Okay, Maxim, can we take one more question? It's okay?
Okay, the last one, okay?
The last one, okay.
Do you know any PKCS11 or HSM?
Do I know what? I didn't hear.
Do you know any
Public.
PKCS11 device, like HSM, on the market that benefits of quantum random generators?
I think, no, I don't know, if to say truth. I don't know if they use it in some crypto schemes for now. For commercial use, I think they don't exist. There exist only the separate quantum random number generators, but the whole systems, as I know, they don't exist.
Okay, thank you.
Thank you, sir. Thank you, Maxim.
Thank
It was
you.
such a